Pronto, Alonso.
Ok. Bom, boa tarde a todos. Hoje mais um seminário do nosso grupo de álgebra. Para fechar com chave de ouro o mês de abril, que tem sido várias palestras de semigrupos numéricos, dado pelo Wanderson, depois pelo Matheus também. Temos aqui... Eu tenho o grande prazer de apresentar a vocês a professora doutora Maria Bras-Amorós, da Universidade de Rovira e Virgili, de Tarragona, não?
Sim.
Maria é especialista na área de semigrupos numéricos e seus trabalhos têm sido bastante importantes aí no avanço da área. E, além disso, ela tem trabalhos também na aplicação de semigrupos numéricos, como na música, teoria dos códigos corretores de erros. Gosta muito dos códigos algébrico-geométricos, não? Sobre curvas algébricas também. Estamos trabalhando aí juntos com a professora Luciane Cus, da UFRJ também. Esteve aqui em Uberlândia no começo de 2020. Um prazer recebê-la aquela vez e ter você mais uma vez aqui, Maria. Agradeço agradeço pela sua presença aqui. Gosta muito do pão de queijo aqui de Minas Gerais?
Sim.
E de jogar ping-pong, não? Então, obrigado, Maria. Deixo a palavra com você. Bom, e a Maria vai falar sobre... A palestra de hoje sobre Asymptotic Logarithmic Behavior of Numerical Semigroups. Maria?
Okay. Thanks for the presentation, Alonso, and thanks for inviting me to give this talk. It's a pleasure for me to be the third in a row after the talk of Wanderson and the talk of Matthews, which I could not follow at the time that they were given, but I could follow them on YouTube, and they were really very nice, both of them. After seeing these talks, this made me think that I could talk also about this theory of numerical semigroups. Today I'm going to present a lot of computational results. All these results led to some new conjectures, but you will see a lot of conjectures but no proof. So maybe after this talk you can have an idea and you help me to prove all these conjectures. That would be really nice and a good excuse to come to Uberlandia once more. Okay, so we define a numerical semigroup as a subset of the non-negative integers. You already saw this in the previous talks. We require 0 to belong to the semigroup. We require the semigroup to be closed under addition. And we require that the complement of the semigroup in the set of non-negative integers is finite. And the number of elements in this complement is what we call the genus of the numerical semigroup. As an example, we can take the hyperelliptic semigroup. For each odd number, like here for 67, we can consider a hyperelliptic semigroup that contains all even numbers up to this odd number, and from this odd number we have all positive integers. It's easy to check that 0 is in the set, that if we take any two numbers here, then the sum is also here, and in this case the complement is the number of odd numbers which are smaller than 67. And in this case, it's 33. Okay. The gaps is, in the theory of numerical semigroups, it's fun because the thing that has a name is the thing that is not in the set. So the gaps are the elements which are not in the semigroup, and in fact, the elements of the semigroup are the non-gaps. This is how things are called. And another example of numerical semigroup is given by by music theory. when we play an acoustic instrument or when we sing a song, when we play a note, there are a lot of notes that sound at the same time at a higher pitch, at a higher pitch, but a lower intensity. Those notes are called the overtones of the note that we are playing, or the harmonics. Here, for instance, you have the set of harmonics that correspond to this fundamental note. This means that when we play this note, all these notes sound at the same time, but at a much lower intensity. So it's sometimes it's not very clear to hear them. If we tune a keyboard dividing each octave in 12 semitones, and all these semitones are equally separated, then once we play one note like this note here, the harmonics that we hear are the notes corresponding to this pink keys. Now we ask what semitone interval corresponds to each harmonic. That is to say, what is the number of semitones in each interval between each of the harmonics with respect to the fundamental. For instance, the difference with the distance between the fundamental to itself is 0, because there are no semitones between the fundamental and itself. The distance between the fundamental note with respect to the first overtone is 12, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 jumps from the fundamental to the first overtone, and so on. This one is at 19 steps, the next one is at 24 steps, and so on. We can put all these numbers in a set, and this set is in fact a numerical semigroup. This has a physical explanation why this is a numerical semigroup. And this semigroup is called the well-tempered numerical semigroup. So we have defined what numerical semigroups are, and we have seen two examples. We have seen the example of hyperelliptic semigroups and the example of the well-tempered semigroup. Now, if we focus on this third condition, we see that the number of gaps is finite, so there's a maximum gap, and this maximum gap is called the Frobenius number. And then we have a conductor, which is this Frobenius number plus 1. The Frobenius is a non-gap, and the conductor is the gap right after the Frobenius number. I don't know if I said the non-gap. I meant that the conductor is the non-gap right after the Frobenius number. Okay. In the case of the hyperelliptic semigroup of genus 33, the one that we saw before, we can draw the semigroup with these circles. We have a yellow circle for the numbers that belong to the semigroup, and we can see that the gray circles are the gaps, and if we count the number of gray circles, we get that we have 33 gaps, and so the genus is 33. The Frobenius number is the largest of these gaps, which is 65, and the conductor is the non-gap right after the Frobenius number, so it's 66. In the case of the well-tempered semigroup, the non-gaps are not so equally distributed as in the hyperelliptic semigroup, but they have an interesting distribution, as we will see later. In this case, the genus is also 33, the Frobenius number is 44, and the conductor is one more, which is 45. Now, we have this property, which is very important, that the conductor is at most twice the genus. What this means is that if our semigroup is enumerated by Si with S0s more than S1, S1s more than S2, and so on, they are enumerated in increasing order, then what this means, that the conductor is at most twice the genus, means exactly that the conductor is at most S sub G. Then what this means is that SG has already G gaps which are smaller than SG, and so SG is necessarily G plus G, because it's the G term plus the G gaps. So SG will be twice G, and from here the elements will grow always one by one with respect to the previous one. We have for any I larger than or equal to 0, we will have that S sub G plus I will be 2G plus I. One way to look at this is that for all indices up to G, we don't know exactly what is the behavior of the elements of the semigroup, but from SG on, everything behaves like a line, and every term increases by 1 with respect to the previous one. So we will concentrate in the first part, in the part in which things do not grow like a line, and we are interested in seeing how things grow before this point. For this, we need to consider the number 5, the golden ratio. You all know this number. It appeared in the previous 2 talks. And this number 5 has many appearances in the theory of numerical semigroups. In fact, the number of numerical semigroups of each given genus grows exponentially by a factor of 5. This was already conjectured in 2007. It was published in 2008, and it was later proved by Alex Zai in 2011. Also, Mateus and Fernando gave very nice results on numerical semigroups, looking at the number of their even gaps, and they found that the number of numerical semigroups of genus 3 gamma with gamma even gaps behaves like something like 5 raised to 2 gamma. Also, in the context of music theory, it was proved that the unique non-bisectional fractal monoid is the one given by fractally dividing intervals by phi. This maybe needs some more explanation to understand, but it can be found in the literature. So we suppose that S is a numerical semigroup of genus G, and consider the set of quotients of the first G elements divided by the first non-zero element. Recall that we enumerated S as S0, S1, S2, and so on, where S0 is 0, S1 is the first non-zero element, and up to SG we don't know how things behave, but from SG everything behaves like a line. So we are interested in this range for I from 1 to G, where we don't know how things behave, and this is what we want to analyze, how things behave here. So we divide any element in the semigroup by the first non-zero element in this range from 1 to G. And then we analyze this set of powers. We raise phi to this set of quotients, and this gives us this set which we will call the set of powers of S, which is phi raised to Si divided by S1 for all I in this range from 1 to G. And this may seem a very a bit strange, but we will justify why we use this definition. First of all, we will see an example of how Q looks like and how E looks like. In the case of the hyperelliptic semigroup, the set of quotients looks like this. It's exactly a line because we are dividing all even numbers by 2, so this just gives all numbers from 0 up to the genus, which is 33. When we take the powers, we are just taking the powers of the integers, so this is just an exponential. But if we take the well-tempered semigroup, in the case of quotients, we get this graph, and this graph looks very regular, and in fact, this reminds somehow the shape of a logarithm, and this is what we are going to see. If instead of the set of quotients, we look at the set of powers, the powers of the quotients look like a line, and this reinforces the idea that this looks like a logarithm, because the powers of this look like a straight line. And this is the aim of this work is exploring how likely is that numerical semigroups, if we take the set of powers, how likely it is that this set of powers is like a straight line. And then we can go back and interpret that these first elements of the semigroup behave more or less like a logarithm. You can, if you have any questions, you can ask. I like questions.
Okay.
Oh, just feel free, okay? So I'm going to explore how much this is similar to a straight line, and the first thing that I thought was regression lines. I am really not familiar with regression lines, so I had to go back to my first courses in statistics and found the formulas and just computed all these formulas. I'm giving you the formulas, but we are not going to the details of the formulas. I'm just interested in the fact that there's this definition of a regression line which approximates a set of points. Here we want to approximate this set of points, the set of points corresponding to these powers. For each I in the x-axis, we consider the point I, comma, the corresponding power. Okay, so we need the mean of the set of powers. The mean of the set of powers is the sum of the elements in the set of powers divided by g, because we have g elements in A of S. Then we can define this regression line. The regression line of this set of points that I mentioned has equation y equal to ax plus b, where A has this formula and B has this formula. The formulas are here, but we don't really need to go to the detail. We just know that they exist, and that the accuracy of the approximation of this regression line is measured by this parameter r squared. R squared is defined like this, and it has the property that it always is in the interval from 0 to 1, and that if r squared is close to 1, then we have very good approximation. The more r squared is close to 1, the better is the approximation. So somehow we translate our question to the question of how far is r squared of the regression line to 1 when we compute the regression line of this graph. Okay, So, for instance, in the case of the hyperelliptic semigroup, we saw that the set of powers behaved like an exponential. So, in this case, if we approximate it by a line, the R parameter is very low. It's far from being 1. On the other hand, if we take this well-tempered semigroup, in this case, the regression line approximates very well the set of powers, in the sense that R squared is 0.99. And we want to see if this is the case in general, for a general semigroup, or if this is just the case of this well-tempered semigroup because it's in fact related to the logarithm. So, now we want to extend the analysis that we did for these two particular semigroups to, in general, the set of semigroups of a given genus. Those two semigroups have genus 33, but maybe they are some kind of extremal semigroups. Let's see what happens if we analyze all semigroups of the same genus as these two. So we fix the genus and consider the set of numerical semigroups of that genus. Ng is the cardinality of Sg, it's the number of semigroups of genus G. And we define the mean of the R squared parameter for all semigroups of genus G. This means that we sum all the R squared parameters and divide by Ng, because the number of semigroups is Ng. And we conjecture that this mean approaches 1 as the G grows to infinity. This is supported by an extensive computational research. In particular, we computed the mean of this R squared parameter for genus up to 60, and we found that this R squared parameter approaches more and more 1. So the interpretation of this conjecture is that for a general numerical semigroup S of a large genus, with large meaning, I don't know, but something larger than 60, there exist parameters A and B such that phi to the Si divided by S1 is approximately AI plus B. Or another way to say is that the ith term of the semigroup is something similar to the multiplicity multiplied by a logarithm, and the logarithm of a line with slope A and constant term B for some pair A, B. So this is why we said, this is why the title of the talk is Logarithmic Behavior of Numerical Semigroups. Okay, so then I'm going to explain now some more computational results related to this conjecture. First of all, once we got the computational evidence that this approaches 1, then we were interested in seeing what was the behavior of the constant term and the slope. We obtained these results, and we could conclude that the slope approaches 0 as the genus grows to infinity, but it never goes below 1 over G. On the other hand, the limit of the constant term seems to be the golden ratio. Okay, and then we can ask a lot of questions related to this conjecture. The first one is why taking phi as a basis. This is kind of a capricious choice. Yes, maybe it is, but we proved with other bases, and we did not find the results so good as when we took as basis the phi, the constant phi. For a general basis, the problem would be the same, except that we substitute the base phi by this general basis, and we can define as before the mean of the set of powers with base b. We can define as before the regression line, the parameters, the slope, the constant term. And as before, we can define the R² parameter for each given semigroup. Then we can fix a genus and compute the mean of this R² parameter for all semigroups of that genus and see what happens. For the case of base B, of base phi, we found that the mean of this R² approached 1. If we take different bases, we get these results here. You can see here we analyzed for base 1.1, for 1.1, for base 1.5, base 1.60, and base phi in the middle, and then other larger bases. We found that the base for which this R² parameter approached faster 1 was exactly the base phi, but we did not try with any base between phi and 1.63, or no base between 1.60 and phi. All this computation takes a lot of time. So all this analysis is really very slow. From this graph, we see that for the choices of base that we took, phi seems to be the best one. Although we can say that for all the bases in this range, the things also seem to approximate 1. Although it's not the case for any base, because for instance for base 10, things if they approach 1, this will be for really large genus. So what we can conjecture here, here is the detail. Since here all lines are very close, I draw here the detail so that you can see that basis phi is the best basis. And we can conjecture that there's an interval around phi such that for any base in this interval, the limit of this R² parameter as g goes to infinity seems to be 1. And also that for any base in this interval, R² is lower, and the limit of R² is lower than the limit of R² in this base is smaller than the limit of R² for base phi. So in this case, it seems that phi is the best option to get R² to approach 1. We said we could change the base, but another question is, what if, apart from changing the base, what if we change the interval where we analyze things? Before I took I in the range from 1 to g, but what if instead of 1 to g I take all elements up to the conductor, or choices? This is what we did next. Again, we define all these parameters, a constant term and the slope, then the regression line corresponding to one semigroup, and the mean of the R² parameter corresponding to one semigroup for this given base and this interval, and then the mean over all semigroups of genus G of this parameter R² over this base and this interval. Natural choices for this interval of analysis are first of all the choice that we already took, which was all the range from 1 to g. But another natural choice is analyzing this for all non-zero non-gaps up to the conductor. this is equivalent to saying the first C minus G non-zero non-gaps, which in this case, for instance, in the case of the hyperelliptic semigroups would be all these non-gaps up to the conductor, or in the case of the well-tempered semigroup, that would mean all non-gaps from the first non-zero non-gap to the conductor. In this case, we repeated the same analysis, and again, everything seemed to approach 1 very fast. Although in this case, if we look at the detail, for genus up to 60, the best choice for a day seems to be 1.63, but it really seems that at some point the blue line will catch the red line. If you look in detail the numbers, every time the blue line is closer and closer to the red line. So this allowed us to make this our conjecture. It's the same conjecture as before, just that we took here as interval, instead of taking all elements from 1 to G, we took all left elements, which means all elements up to the conductor. So the conjecture is that there's an interval around phi such that the R-square parameter corresponding to the regression line of, recall that we are approximating by a line that set of points. So the line has the accuracy is this R-square parameter, and what we say is that the mean of this R-square parameter corresponding to all bases in this interval around phi, when we consider elements of semigroups up to the conductor, this also approaches 1. And again, although for all these bases in this interval, it seems that things approach 1, still phi, we conjecture that phi is the one having highest R-squared parameter. Although we did not find a genus for which phi was better than 1.63 with respect to these left elements. But I would say, looking at the looking at the numbers and looking at how the numbers corresponding to phi approach the numbers corresponding to 163, I would expect that around genus 75, the phi would catch 163, but this is impossible to check right now with the computational tools that we have at the moment. So this is just a conjecture, no proved results, so open questions. Another question is, why do you start by the first non-zero element? Why don't you start by 0? And if instead of starting by 1 we start by 0, things seem to behave more or less similarly, although the approximation, the behavior seems to be more logarithmic if we do not consider 0 in the set. And finally, when I was intrigued by this logarithmic behavior of semigroups, apart from looking at the regression lines, I saw that there was something called logarithmic regression, and I thought I had to prove what this logarithmic regression meant in the case of these numerical semigroups. But logarithmic regression is something different than what I explained before. In this case, we are not approximating a set of points I, y, I, but a set of points log I, y, I. So, in this case, we consider this set of points and compute the regression line. So, we approximate the values of the semigroup by a model of the form the ith term is equal to a log I plus b. This is different than what we had before. If I go some slides, some previous slides, what we had in the computations that we did is that Si would be something similar to S1 times the logarithm of a line. And in this other logarithmic regression, what we have is a times a log plus a constant, which is really different. So now the choice of the base has no effect on R squared. We compute R squared in a similar way as we did before. And we also proved what if we take only the left elements. We observed that R squared is still very close to 1, but it slightly decreases with the genus. You can see the graphs. In this case, for the logarithmic regression, we have values which are always among 0.9, but they go decreasing clearly. And that's all. That's all I wanted to explain today. Thank you very much.
Obrigado, Maria. Now, questions, comments, objections. Pietro.
Proofs.
Sorry, it was late. Yeah, great talk. It was very interesting, but I have no questions. I'm sorry.
Ok. Pode perguntar em português. Mariana, se tiver alguma pergunta.
Também não.
Hi, Mariana.
Hi. Naquela hora eu achei que o áudio estava aberto e eu estava aqui dando oi.
I'm not understanding at all.
Maria, bom, eu tenho uma... Vou te fazer a pergunta em português. Você comentou algumas conjecturas, não? Agora em relação a essas potências, não? Mas eu vi que essas conjecturas, bom, eu não sei, claro, você sabe mais, estão diretamente relacionadas com as outras que você tinha falado do número de semigrupos, assim, no sentido de que uma resposta de uma consegue a outra ou não tem, a priori não são completamente...
No, I don't think they have anything to do. No, here, because here we are looking at the shape of the semigroup when we graph it, but we are not counting semigroups, or no, we are not. I don't think it has anything to do.
Because when you define the R squared, you use the n over numbers of numerical semigroups, no?
No, but this is just because I'm computing this R square over all semigroups, and then I sum everything, and then I need to divide by n. In order to get the mean, then I need to divide by n sub g. But just because I'm computing this parameter over all semigroups of genus G, and then I'm taking the mean of it.
Okay. Questions, comments, objections, suggestions?
In fact, I think that my talk was a lot of questions. Maybe you have answers.
Do you have some idea to attack these conjectures?
No idea.
No.
I have no idea. somehow this makes me think that numerical semigroups are like a discrete version of logarithms. In fact, this well-tempered semigroup is, you obtain it by discretizing the logarithm. If you for each I, you compute the logarithm of I. This gives you a sequence, and this sequence is a sequence of real numbers. If you multiply everything by a constant and then take the floor, then this gives you this this well-tempered semigroup. But my surprise was that the mean, if you take for genus 33, you take the mean of this R squared, and it's even higher than for the well-tempered semigroup. I thought that the well-tempered semigroup would be an extremal case, and it's not the extremal case. I'm afraid now about the question, what is the extremal case, but because I don't know. I think that's a good question. But the well-tempered semigroup is not the extreme case.
Ok. Algum outro comentário?
Alô?
Ah, Cícero. Agora estamos ouvindo. Não, paramos de ouvir já.
Tá me ouvindo aí? Não.
Ah, agora sim. Tá cortando, Cícero.
Ah.
Agora.
Ô Cícero, tenta tirar o fone, que às vezes atrapalha, já aconteceu comigo. Tenta fazer só com... Tenta tirar o fone de ouvido e fazer direto do computador, às vezes ajuda.
Tá ouvindo agora ou não?
Ah, agora sim.
Okay. So maybe that base is phi, because that the phi number is related to the growth of the number of semigroups, right?
Mm-hmm.
And of course, this probably is related to the, how can I say this? The possibility, you take some n, say n sub 5, and you have some possibilities for n sub 5 to be between n sub 4 and n sub 6.
Mm-hmm.
So maybe this is why the phi, maybe this somewhat is related to phi being a good base for the log, because it is related to how those numbers have to fit inside each other to be a semigroup.
Mm.
No, it's just an idea. I'm not sure if I was very clear.
I don't think I got this last point.
Because let's say you have the growth of the semigroups, a rate of growth, and but you can't have that suddenly. For example, n sub 5 jumps very far away from n sub 4, because you would have other semigroups between the first and this last one, where n sub 5 is far from n sub 4. So as the semigroup changes, there must be maybe a range for where the numbers may be, n sub 5, n sub 6, in related to each other, in relation to each other. So maybe it's just a strange idea, it means nothing. But maybe from now to 6 months, you wake up and you say, that's why the crazy guy meant.
Maybe. Yeah. Directly, I don't see any relation between one problem and the other one. It's like a surprise once more than the phi number is there. I have to say that when I studied mathematics and they were always talking about this number, I was kind of skeptic about this number. But no, I cannot be skeptic anymore. It's I found it in three very different problems. This one of the growth, this fractal division of intervals, the only fractal division of intervals that gives you a monoid that is closed under addition is when you divide everything by the golden ratio. This is also a completely different result, and these are results and these results are on the shape of numerical semigroups. Yeah. I don't know. I think it's difficult.
Okay.
So maybe it's an excuse to come again and discuss. Or an excuse to have Mariana here.
¿Algún otro comentario? ¿No? Okay, thanks, Maria. Thanks very much. Okay, então. Muchas gracias. Muito obrigado.
Muito obrigada, yo. See, I'm sorry that I cannot speak Portuguese. Thanks for inviting me.